Hello calculus students. Today we're going to continue working with power series. Specifically, we're going to start to try to engineer power series to accomplish some fairly trivial at the beginning goals, but this will give you an idea of how you can use them to achieve modeling a function in a certain region. So there's two different methods we'll be looking at in this first video in order to model a function with a power series. The first one is kind of contrived, but there's a couple problems in your assignment, so I'm going to do one like that. And it's also just a good example to extend a technique that you've done in the past. That's long division. But most of the time for this section, we're going to be using geometric series, or the theory of geometric series, in order to model functions with power series. Okay? So this guy can be done either way, so we'll come back at the end and do it with geometric series as well. All right. So 1 over 2 plus x is the function that we want to create a power series model of. Does that kind of make sense as the goal? Same kind of thing over here. We're going to create a power series model of that function, and that function. You can see that all these functions share some things in common because we're just going to be working with similar types of problems today, and then tomorrow we'll try to broaden our horizons a little bit using these approaches. Okay? So they're all nice rational functions. I wonder why that is. So this guy is a division problem, right? So we could actually do long division on it. You've just never done long division on a problem quite like this before. Because what goes where when you do the long division?
You have 2 plus x.
What's going to go on the inside?
1.
1 is being divided by 2 plus x. So that's a little bit funky. Usually when we did polynomial division or division with variable quantities, the higher degree polynomial went inside and the lower degree one went outside, right? It didn't make sense to really do it the reverse way because we never really thought about actually trying to divide this before, but now we're going to, okay? So think about the same way you've done long division in the past, it's just a little bit weirder now. So the way we do it is we think about this stuff, or the first thing of this stuff, times what gives me this, right? So 2 times what gives you 1. It's not too hard.
1 over x.
It's 1/2, right?
Oh.
So you say, okay, that's 1/2. That's the first number in my quotient. So then what do we do with that 1/2 when we did long division? We don't just distribute it times 2, we also distribute it times x, right? So we go, half of 2 is 1. We knew that was going to happen because we made it happen. But then we also have a side effect, a little extra 1/2 x right here. And of course we always write our minus in long division because of the pitfalls if you don't.
Could you have also written
So I don't think I'm done yet. That's just the first term in my power series function solution. Okay? So, sorry, I'm going to keep going for a bit. So now I need to do this again, but I need to know what's left down here first. So how do you get what's left down here?
You subtract. It's negative 1/2
You
x.
subtract, but what is this? What is subtracted? Technically,
Because it's plus 0x.
I could put plus 0x, exactly. And I could put plus 0x squared and all that other stuff. You guys starting to see the power series maybe? Maybe not yet. Let's see. So we have 0 minus 1/2 x is going to be negative 1/2 x, right? And then if you're already thinking ahead, what am I going to put right here for the next term?
Plus 0x squared.
Plus 0x squared, which is going to fall down to place here. I think we'll need to do a few terms before we can build up the power series. So now I'm going to repeat. 2 times what gives me negative 1/2 x?
Negative 1/4.
Is it negative 1/4? You
X.
can always distribute it back through, right?
X.
I need an x on that one, don't I? Because now negative 1/4 x times 2 will be 2 1/4, which is 1/2, and negative and x.
And you add it.
But then we'll have some side effects, some other results. So we're going to have minus 1/4 x squared right there. Subtracting this, 0 minus negative 1/4 is positive 1/4 x squared. Let's just do one more step so that we can see our power series. Can you see it starting to develop up here a little bit though?
Yeah.
Probably need at least 3 or 4 terms to decide for sure. Okay? So now I'm going to have 0x cubed. 2 times what gives me this?
Negative.
Is it an eighth?
1/8 x squared.
Negative?
No, it's not negative.
This is positive, this is positive. So I think it's positive 1/8, and we of course need an x squared there then. So again, we distribute and just repeat the process. We'll get 1/4 x squared here if we did it right, and then we'll get 1/8 x cubed there. When we subtract, this is going to be minus 1/8 x cubed. And we could keep going, but you can see that this power series looks like it's going to alternate. And I think I can see the pattern. Can you guys see the pattern?
Yeah.
What's the next term going to be if we keep going?
Negative 1/16 x cubed.
Yes. So as soon as you can see the pattern, I mean, the battle's pretty much won. You just need to condense it from its expanded form into its abbreviated compact power series notation. So this guy, in other words, can be represented by a power series of what? What have we got there? I'm going to put plus dot dot dot. Should we start at 0? I'm thinking of starting at 0 because that'll be a nice way to get a constant, the first thing.
1/2 to the n.
1/2, and it looks like the powers are decreasing on the bottom. Yep. So if we put 0 there, we'll get 1. Ooh, that's not quite right, is it?
No, so it needs to start at 1.
2 to the n plus 1.
Yeah.
We could make this different ways, right? Like, there we go. 2 to the n plus 1 sounds good.
Times x, or nx.
X to the n is pretty simple, I think, or not? If I put
Minus
0 in
1.
there, is it going to be a constant?
It used to be minus 1.
Yes. When I put 1 in there, it'll be this. When I put 2 in there, it'll be this. 3 in there is going to be this. When I put 1 in here, it's going to be, it's supposed to be a fourth, right? Is it going to be a fourth? Yes. What's the only other thing I need?
The alternator.
The alternator.
-1 to the n plus
We
1.
could probably just put it in the 2,
Yeah.
or we could make it separate, like up here. And do you just want to go in plus 1 there
It's
too?
just n.
No, it's not.
If we put 0 in right now, it's going to be negative. The first thing's positive, so I think that it should be just n. So that's one version of the power series that is that function. Pretty crazy, huh? And we accomplished that with long division. So you'll have a couple problems like that in your assignment to practice, but the bulk of the assignment is going to be about using geometric series to do the same thing. It's a little bit easier to manipulate, especially if you want to move where the center is. Okay? So I'm going to leave that up on the board, at least the result, so we can come back and do it geometrically and see if we get the same thing in a second. Okay? So, reminding you about the basic facts of geometric series. A geometric series is where you have a common ratio from one term to the next when you're adding up the terms in the series. Looks like this, right? We usually start indexed at 0. If we want to put a 1 here, how does that shift it?
Subtract a sub 0.
That's going to be less terms, less by 1, so it's going to be n minus 1 power there, right? So hopefully that should start to make sense more since we've been shifting indexes as well. And so the geometric series, as long as r is less than 1, as long as the ratio from term to term is less than 1, it's going to converge. And this is what it converges to, which is pretty crazy because most series we haven't figured out what they converge to, we just know whether they converge or not. Since this one we know what exactly it converges to, we can use that fact to model a lot of different power series. So here's a nice, really simple one that you can basically use it directly on. Can you guys see that relationship in this function?
Yeah.
Sure.
It's like pretty much exactly right. So here we have a, if we model this with geometrically, a is going to be what?
1.
This one, and r is going to be equal to
X.
x, right? So we're just going to say this equals the series from that result, starting at 0, just like that result. And we're going to say this one is a, and r is x to the n. Done. That's the compact form of that function as a power series. And of course, we really don't even need the 1. It's just the series of x to the n. Which of course you could write in expanded form. I've been talking about the importance of navigating between compact form and expanded form, or in other words, x to the 0 plus x to the 1 plus x2 plus x cubed in this example. And of course, then that would be 1. And that would be x. So don't forget that lesson as we move forwards. But we're pretty much done there. This power series, I don't think, converges to that function everywhere, though. It only converges where that power series is convergent. And where is this power series convergent? We could use the ratio test, but hopefully by now you've started to think about where the centers of these are and kind of shortcut in your head what the ratio test results are. So where's this guy centered?
0.
At 0.
And
Okay.
it's convergent between -1 and 1.
And because of this, it's going to be convergent where the absolute value of x is less than 1. So that's all we know for sure. Maybe one of the edges, maybe both of the edges, maybe none of the edges converge, but we at least know the radius is 1 and that its center is 0. So your question is, or a natural question you should have at this point is, well, what if I don't want to calculate f of 0.5? What if instead I want to calculate f of negative 1.5? Could I do it with this series? No, because it doesn't converge in that area of negative 1.5. So would you be completely out of luck?
No.
No, you just need to transform that series to go over by negative 1.5 now. So I've said, let's just stick with that same function. But let's engineer the interval. Instead of being centered at 0, like this one was centered, looking right there, right? Let's center it at negative 1 so that we could accomplish a calculation like negative 1.5 using the series.
X plus 1.
Right? Because that's how our calculator does these kinds of things.
Just x plus 1 to the end.
So all you've got to do is manipulate this algebraically using rules. So this is where some of the cleverness of the assignment comes in. This is good stuff, algebraic cleverness. So I'm going to take that 1 over 1 minus x and manipulate it until I get the right center. So I have to start with that, but I can do any kind of clever 1s or clever 0s to make it happen. Yeah? So what I like to do is say, hey, well, that's x equals 0. Instead, I'm going to go minus, you know what, I need x. To get centered at negative 1, it's got to be x plus 1, like so, right? Like that's what I need to shoot for, do I not?
Yeah, you need to shoot that. But that's not
So that's what I need, but I need to make it out of this legitimately without actually changing what this is. Can I make that happen? I've got a negative x, that looks good.
Make it 2.
So this says negative 1, but we need this to be 1, so Carson is right. You can call that 2. Technically, what did I add on the bottom there?
Clever 0.
I added a clever 0. So any kind of legal, legitimate algebraic manipulation is how you kind of get this done. And we'll include derivatives and integrals to make this happen tomorrow. But today, we're just going to do simple algebraic clever 1s or clever 0s. So that is that. If you're not sure, look, distribute, and you'll see that you get back to there. The point is, now this is centered at negative 1. So can I go and use my geometric form now?
No,
Not quite yet. Why not?
we don't have 1 on the bottom, we have 2.
We need a 1 right here, not a 2. So if you're like, well, crap, I needed the 2 to make it do this. You're right, but we can do something else.
Just divide it by 2.
If we divide this by 2, we'll have 1. So the side effect would be
X plus 1.
I'd have to divide everything else by 2. It's kind of like a clever 1 now, right? Like I could think about doing 1/2 right here, and that'll make that by 2, but I'm going to apply it to the whole bottom, right? But if I do something there, that's going to be illegal unless
Flip 1 time.
I balance it up here, and then I can just cross that back out because it's really just a clever 1. Okay? So I'll see what happens, and it looks like I'm going to get 1/2 on top now. If I distribute this, I'll have my 1 that I needed to match the geometric form, and then I'm going to have this go x plus 1 over 2, like so. And so I like to put my parentheses there to show that this now matches the geometric form of a over 1 minus r. That's how it works. So now I'm going to say, all right, that can be built into a series starting at 0, going to infinity, of course, where a is 1/2 and r is x plus 1 over 2 to the nth power. Which then, of course, if I wanted to, as my calculator uses, I could write an expanded form and go, if I put 0 in, that's going to be 1, so it's 1/2 plus, if I put 1 in, it's going to be 1/4 x plus 1, next one's 1/8 x plus 1 squared plus ... The whole point was, don't get lost in the details, remember the big picture. This was the same function. This was me manipulating it to have a new center. Where is it now centered? At -1. And you can look right here to decide that, or you can remember what you did. But going back to the compact form, so I'm going to, you know what? I'll just leave my expanded form up. Looking right here, I basically, when you do the ratio test, you're going to get, or if you just use the geometric series test, right? This is r, and it's got to be less than 1. That's what you'll get either way. And so the radius on this one is not 1 like originally was. Now the radius is 2. So I kind of get an extra benefit here. By this manipulation, I've got a larger radius, and it's also centered where I want. So if I want to compute, like, going back up here and say, what is f of 1.5? I can go down here and say 1/2 plus 1/4. Or I was thinking negative 1.5, right?
Yeah.
So that would be like, because that's definitely inside this interval now. So I can say, well, it'd be 1/2 plus 1/4, plug in negative 1.5, plus 1/8, plug in negative 1.5. Do that to enough terms, and that's what the calculator is doing when it does something like this, at least most of the time. Okay? So we've learned some pretty powerful stuff now, I think. Let's do one more problem. If you're watching the video, at this point, this is one of the last couple problems we're going to do today. I think you're pretty warmed up to try to figure out this one yourself. So I'm going to pause it for my students, then we'll come back and work this out. Come up with a geometric representation, geometric power series representation of the good old function just 1 over x. Pause it and try that out. All right, so a moment ago, I asked my students to figure out how to take it the next step and figure out a power series representation for the good old-fashioned 1 over x parent function. What I didn't say, so you might have had an answer different than mine, is where you want to center it, because we could engineer various different centers. So I'm going to show an example where it's centered at 1, and so you should have the same thing as me if yours was centered at 1. If yours ended up being centered somewhere else, coincidentally, it might not be exactly the same function representation. So the fact that I want it centered at 1 kind of gives me a clue as to how to start the problem. So I know I need to have 1 over x. So if I want it to be centered at 1, I'm going to have to manipulate this. This is now centered at 0, looks like to me, or something like that. So if I want it to be centered at 1, I know I need this pretty much, right? I need an x minus 1.
Yeah.
So then I'm going to be like, all right, so, well, the only way to make that happen is to have a plus 1 out here, right? That's the only way to make that legally true. So then I'm like, okay, but, so this matches the geometric form except for the minus. So I need to change that from plus to minus, but I need to keep this intact as positive 1 as well. So how am I going to do that?
You can do it in 2 steps by multiplying by clever 1 of negative 1. And then
so that's kind of where I have to be careful here. So let's see. If I go like this, there's different ways to think about this, but I could go, all right, well, I could write this as minus minus for 1, couldn't I?
yeah.
Does that work? I mean, does that accomplish what I need?
I guess.
What's the other way?
It would be to multiply by a negative 1.
On the top and the bottom?
Yeah, so you get negative 1.
So
over
that's one attempt. If we go like this, try to color code it, then what are we going to have?
A negative 1 over negative 1 minus x plus 1.
But that causes this problem right there. So I don't think that's going to work, is it? So I think that's wrong. I don't think that's the way to go. I think what I had is the way to go. So where we went to here, right there, we said you could just go 1 minus a negative, like so. And so I think that's the way to go. So we're going to have 1 minus, and then this guy. I can distribute in there or whatever. So it's going to be negative x plus 1. So that's one way to do this guy. Okay? So now I can say that's equal to the series starting at 0, the first term of 1 from that one, and an r of negative x plus 1 to the n power. And now if I'd like to, I could play around with things I know about series expressions and reduce this. For instance, how could I mess with that a little bit? Like if I don't like this negative on that x, that's cool. I can take it out. How? I could say, well, this is the series. And then think about the negative one. Maybe I'll use a bracket to be clear here. like this. All to the n power. And then that n could be distributed to each part, could it not? So I could say -1 to the n could kind of come out here, because that's not really doing much, making much of a difference to begin with anyway. And then I'd have x minus 1 to the n power back inside. So that might be a little bit better way to write this one down. And so since that worked like that, there were other ways to do this simplification up here as well. But does that guy clearly look like it's centered at 1, like I asked it to be?
Yeah.
Yeah, it definitely does. We could do the ratio test to figure out what its radius is. I think its radius is 1, too, though. There's nothing that's going to change that radius. So going back to the first problem that we opened with in this video, the long division problem, where we came up with this result, I thought it would be a good idea to clarify that result, since this looks pretty geometric, and see if it matches that way as well, or at least it should match pretty close, and we can manipulate it. So, if I did this one geometrically, I'd start with this function and say, well, I need to have a minus, need to have a 1. So I decided to do my minus first by using the double negative, just like I did on this problem. I think I'll get this out of the way now. And then I said, well, I want this to be a 1, not a 2, so I'm going to divide the whole bottom by 2 and the top by 2 with a nice clever 1 there. And now I think it matches the geometric form of a over 1 minus r. So this would be the series starting at 0 of 1/2 for the first term, and this is r to the n. So look at that and look at that and tell me, are they exactly the same? So we have a negative x to the n. Not quite, but couldn't I put this, since these are both to the n, couldn't I rewrite this one as, and put those both to the power of n, -1 and x?
Mm-hmm.
So that's accounted for. Now here we have 2 to the n and then an extra 2 on the outside on the denominator. And here we have 2 to the n and then
Extra 1.
an extra 2 on the outside on the denominator. So I think these are exactly the same. Two different ways to come up with the same power series model on that one. The last one I want to do in this video is a little bit more involved, and it'll allude to problems we'll look at tomorrow. So here we go. This function is a little bit more complicated, a little more complex. Do you guys have any idea a first step that we might use before we apply this power series
Long
stuff?
division.
You could use long division, or you could use something else that's a ubiquitous tool in Calc 2 and beyond. Can you rip apart that function and simplify it somehow? First of all, couldn't you do this?
Factor double. X plus 1 minus 2.
Why would you want to think that first?
Oh, because, what's it called? The, parts.
Partial fractions,
Partial
right?
fraction.
And then once we have the partial fraction pieces, think about these partial fraction pieces once we get them. What do they look like? What do these each look like right now? They both look geometric to me, because we can make them geometric real easily. So let's do the partial fractions. Good review of that anyway. Partial fractions can be used for many different things. I hope you're starting to understand that. So, don't we go 3x minus 1 equals ax minus 1 plus bx plus 1 from this equation right here. And then we say, what's a convenient value we should choose to do this the easy way? One of them is not a, right? X equals 1, because this has to apply for all x values. When I plug that in here, I get 2. When I plug that in there, a drops out. When I plug that in there, I get 2b. So b equals 1. My other convenient value, luckily I have 2, is -1. So when I plug that into the equation, I'm going to get -4 equals, that drops out, -2a. So a equals 2. So what I've got so far is that this function is the same as the function 2 over x plus 1 plus the function 1 over x minus 1. That function is this function decomposed using partial fractions. And so now I can say, hey, those both look like power series, do they not? Those both look like geometric series, I should say. Which one's the most obvious? I think this one
Yeah, I
is.
think that one is.
Because if you just rewrite it as 2 over 1
Minus negative x.
minus negative x, it fits the form, doesn't it? That's the same. Plus is minus minus. That's ready to go. And now this one we might need a little more help with. Let's see, 1 over...
Negative 1 plus x.
Should I factor out a negative 1 down here? I think I'm gonna. And then I'm gonna write one more step. You know what? Can't I pull this negative to the top now? So that's what I'm going to do. I'm going to move this up here. So now I have negative 1 plus x down there. What's the problem with that?
You're adding
Did I
x.
make a mistake? I think I did. When I pull a negative out, so I had x minus 1, pull a negative out.
Yeah, you can do that.
Hold on. I'm being dumb with negatives today. So for some reason, this isn't that, right?
This isn't, wait,
Who's clever one?
no, plus 1.
I screwed up
Has to be plus 1.
because we're trusting me too much. So let's back up a step. So this wasn't right.
That was close,
So
right?
it's going to be 1 over
negative x plus 1.
negative x. That will be the same.
Yes, it will.
I'm going to pull out the negative 1 and say, then this is positive 1 for that, minus x for that. Yeah, good. Thank you, Ethan.
Negative x plus 1.
Now I'm good to go, and now I can put this up here like I was saying, right? And so I'll have 1 minus x, done. Sweet, those are both geometric, so they're both ready to write as series. This one is the series starting at 0 to infinity of the first term is 2, and the ratio is negative x. And this one is the series starting at 0 and going to infinity, first term 1. You know what, I'm going to be consistent with how I'm using my parentheses, and the ratio is just positive x. Does that make sense? And so, of course, you can put those series together. Since they're indexed starting at the same place, I've always got to check those indices. And so we've got 2 negative x to the n minus x to the n. And so could we continue to simplify this guy?
Yeah.
Any other steps that might work?
You can pull out the alternator and the negative x.
So this would be like negative, should we just put the alternator with the 2? I'm thinking of that. Maybe negative 2 to the n, x to the n, minus x to the n.
Does that work? Because you're pulling out negative 1 to the n times 2. That's not the same
Ah,
thing.
the 2 isn't to the n, you're right. Good point, thank you. So we've got negative 1 to the n, and then times 2. And so we could like factor out the x to the n if we wanted, right? So my last step might be this. But you have the idea, right? So I'm going to say x to the n. And I'm going to say 2 negative 1 to the n minus 1. That looks pretty nice to me. So there you go. Today you learned how to model series, or excuse me, model functions using power series. I'll see you next time.